Okay, so this is Jeju Island. It is like 1.5 island area of Oahu. So it's like the size of the island of Maui. And basically the Hala Mountain is here, the highest point of the island. And this is the eastern sector, which has lots of water use, and there is salinity problems in this area. So if we take a cross section A, it will look like this. This is the conceptual model now, right? The conceptual model. We have different layers above out. This is a more water-bearing aquifer, unconfined aquifer. But it has two formations, CU formation and U formation, which are very low conductivity material, and the basement, which is basically low conductivity. So we can treat this as basically the boundary of the bottom of the aquifer. That's what we did for seawater, but for mud flow, we took it here with low conductivity material. And this is ocean, and basically there is this cones which create some kind of different conductivity for the basalt. This is, if you come close to the ocean, the big difference was that we have a bottom. We have a bottom for that. Because for a while, remember, we needed to set the boundary at the bottom, but this one is already known. So they call this basal water here, and there's transition zones, fresh salt transition zone here. Then this is basically the fresh groundwater of the Weibo formation here. And they call this para-basal, which we don't have that in Oahu. And this is like, supposedly the guidance has it, but it's less than 40 in some locations. So they have high level water here, which is not well understood. And basically this recharge goes to the water table here. Okay? So conceptual model, you need to know all of that to feed into your model. So here is this basically why I want to give you this model, because you could use two different models or two different methods to use whatever your purpose can be different. Like we use mud flow, which does not include salinity, to assess water levels and spring flows for the whole island. Okay? So we set model for the whole island, similar to what I described about water. Okay? So that mud flow does not include salinity at all. Then we use seawater only to do it for the eastern sector, where salinity is important. Okay? So we just chop the spot and did the modeling using seawater, which includes density effects. So here is the mud flow model, very similar to water, right? We have here the 40 to 1. So this is different layers with different conductivities. This is the basement to assign very low conductivity here. And this is, we chopped it at certain value at the bottom. I don't know why we glued it anyway, but we could have stopped at this line here. And I call this the donut moment, the donut. Yes, the donut moment. Why? Because we don't understand what is happening in this area here, okay? So we don't have data, we don't have any conductivity information, we don't have wells to tell us what's the water level. So why should we worry about it? So we cut this area here, but basically whatever recharge is falling here, we route it to the model, okay? So basically water from this area and we route it to the rest of it. So we just got the water input from this area to the rest of it. Is that acceptable? Yeah. I mean, We could have spent lots of time trying to calibrate the model but we don't have any data to calibrate it, so why worry about it? You know? What we need here is to set the conditions, the boundary condition here, to describe whatever water coming or feeding the system. So that's what modeling tricks, right? As you do things, you learn how to be creative. So we do scenarios, right? Because remember we talk about land change, we talk about climate change. So we have here the baseline recharge, which is the current. Like this is a distribution of recharge for different area. By the way, they use these areas as management areas. We divided the management areas to 3 sections, but this basically how they manage. Remember the aquifers of all same systems, but they're not exactly physically based, it's just a use for management. Then we assign recharge based on available information. Then we did the climate change models, which include different distributions. For them, it was most likely to have a change in distribution. Not big drop in recharge, it's just a change. In some areas get drier and some areas get wet. But we include land use changes in this one. Then also include land use change and the drought. Okay? And we use historical data to decide on what drought condition, and that was, as I will show later, much worse than climate change effects. So while we have one scenario for recharge, but here we have 3 scenarios. So here's what calibration for mud flow. So the black lines are whatever data available. Okay? So somebody collected data from wells and draws the black or gray contours here. Like this is the 2 meters and the red is our simulation. Is that close enough? Yeah, it's perfect, right? But that's what you can get, the best you can get. Because can you see the 2 meter contour here? It's very difficult to get it to match unless you really narrow down and change conductivity in this area to force it. But there is no evidence to support what you do, right? So it would be like, yeah, tweaking, but too much, right? Because you don't have support to do that. So basically, on the average, yeah, it's not too bad, right? So that's basically very subjective, you know, if this is good enough. And this is the donut part, the exploded part, which is stopped at 200 meters. So the blue line is the 200 meters, light blue is 150 and so forth. Then this is the criteria for calibration. We assign conductivities and change it manually to make sure we get this results. You can see it's a tedious process, right? So, you know, we found out good indication is that with the cones exist, conductivity should be low, which was okay, you know, like all this low conductivity areas coincided with cones. And here's high conductivity in areas which don't have. So again, qualitatively, yeah, it looks easy. You could do better. Actually, mud flow or the package for the automatic calibration, you can get very, very detailed conductivity to give you the match. But you have to have justification for that. You can't force the model to give you what you want by getting conductivities at very small scale, you know, like contour it would be very colorful map, but you need some justification for it. So here is C1. So now C1 is for density part. It's only for this portion of the island here. Okay? So just this eastern section. Why? Because C1 is hungry for data and for execution time. It takes too much. And also, if we cut the whole aquifer to cells, the cells has to be small. And C1 cannot handle a very large number of cells. So we did it only for starting from the dotted line until the short line. Why also, this was another justification, because most of salinity problems are in this area here. So here is a cross section for this area, which we accounted for different material. Here is a basalt and there is a two conductivity. So we excluded the basement. So here is a calibration. And it was interesting, we found that conductivity was reasonable. It matched whatever mud flow required. So this is a 2 meter contour, the 10, the 50, 100, 150, and 2. But you can see some inaccuracies, especially in these areas here. And we use salinity data to calibrate for salinity. And you can see this is fresh, and this is ocean, and these are the numbers. I don't know if you can see them, but they are reasonable. You know, this is 13 compared to 19 for ESO. And the errors are here, here, and here, mostly where we don't have enough modeling for the hydraulic head. Okay, remember the previous one? These are the areas where we have less accurate results. And this is basically the salt water wedge. So this is salt here, and this is brackish, and this is fresh water, which is typical for areas where you have a basement, where you have no flow at the bottom. And this is the water table. So that's the model calibrated, then you do it for scenarios, and this is part of the scenarios. Remember, the criteria for sustainability was spring flow. So we did here to see what will happen under different scenarios. So this is for baseline, the circle, which is current. For climate change is the squares. For drought for 5 years, the triangles. The dark triangles is for drought for 10 years. And this basically, this is using too much, right? Sustainable yield is what you're allowed to use. So I am using 20% of that, 40%, 60, and 100% of sustainable yield. Then what you see here is the decline in the average base flow change. So basically the current is here. Anything worse than the current give you decline, right? Like here is, I have increase in base flow. This is the current spring flow here is 0. So here this is positive, right? That means good. But starting from here, even with the baseline, I am having a decline in spring flow. And of course, anything below 0 is bad, right? So anything below this line is bad, right? So if you want to go for like 60%, then almost everything is bad except the current, the baseline. Okay, so that can help the management, right? If you want to make a decision, then you say under current condition, I cannot use more than 60. Or if we have climate change, I cannot use more than 40, right? And so forth. Then in the second plot, we counted how many springs will become dry. That's worse, right? This number of springs dry. So this is the current one. And any change here will increase the number of dry springs. And of course, long drought is the worst. Long drought is the worst. Then this is with the water level. Again, this is the current water level. If you use more, the water will decline. Water level will decline. And if any of the other scenarios worse, right? So we have more decline. And you can see it changes. Maybe this one should have been below, but it's because this is average. You know, some areas got worse than others. This is just to give you the contour maps of hydraulic head at different scenarios. So this one is at climate change with different use. So this one is only 18%, this one is 51%, this 84% of sustainable use. So you can see if you look at the 2-meter contour, this is here, it will move inland, right? We the decline, right? Move the things, the lens is shrinking, and this one is shrunk much more. And this area is very sensitive because there is too much use and there is lots of, the layer is very thin as well.
What does that mean when you say climate change? What kind of variables are you talking about?
We talk about there is climate people, they give us their simulations.
Mhm.
They use like either downscaling or statistical approach to
Mhm. decide
what would be rainfall rate, temperature, things like that. So you can predict how much recharge.
Mhm.
So this is very active area now. I try to show what's the likely effect of climate change on basically recharge. That's the main issue.
So some other modeler then did a certain climate change scenario, presumably warming,
Right.
and they come up with a recharge that you use to plug in your model.
Exactly. And this is also the scenario for salinity. This is a baseline now. You can see all below, that means fresh. But if you have climate change, after climate change, you see it's now start to become salty in this area here. And it is worse if you have 10 years of drought. Okay? You can see the fresh water is gone in this area. Okay, that's now the interesting, difficult part.
Are you going to leave Korea or come back?
We're done.
So did you presumably come up with a SGD type flux around the margins? Did
No, they were
no.
not interested in that. But basically,
I mean, you have that data, right?
I have the model here.
Yeah.
But basically, we can use C1 to estimate the CCG.
You would
But-
have to do that next? You didn't do that? Or
No, we did not, because it wasn't really part of the objectives.
But then,
Are you interested?
Again,
well, you have a
papers.
Korean colleague that I met in your office that works
Yeah.
on SGD, right?
Yeah, I think I mentioned that when they were.
Yeah.
Was it? Was it?
He was here in April, but we met in my office. I gave him a few.
Yeah, I know, but this is straight.
Oh, I don't know.
Okay, so to just build up on what you just said, so we can use the models. Basically, you click over the boundary, okay? That's where water exit, right, at the shoreline. You click over the line or the coastline or the basically bathymetry area outside in the ocean and estimate how much is this GP. So you can estimate it for the area, boundary arc or polygon, or cell by cell. Remember, we cut off the cells, so you can estimate how much water is leaving each cell. And uncertainties are related to the model, okay, because data is not perfect and calibration is not exact. But there's also things which Henrietta talked about in her presentation last week, right? There is lots of uncertainty about the SCG. But the bottom line, the most important one is, are we simulating what we are measuring, right? That's the problem. I can run C1 and give you numbers, right? I can give you values of fluxes. I can give you salinities, right? But do they represent what you are measuring? That's the question. Just to give you an example, this is in Kyoto, so here is the aquifer itself. Okay. So this is a coastline. But we need to extend it a little bit to the ocean because SCGD can exit from this area here, as well as the coastline. And we could have boundary condition here. We call it the ocean vertical boundary, and the ocean bottom boundary, and the coastline. So you need to set the conditions here that's required to run the model. And actually, we are not sure about the modeling results. Of course, we are sure about the field data. So what we have here, the circles are the measurements, right? Radon-based measurements. And you can see the tides. The black lines are tides. And they are, as Henrietta explained in the lecture, they are reversed. So the highest SGD coincide with the lowest tide and vice versa. Okay. So that's really reasonable. And the modeling is gray, okay, which seems to match, not too bad to match with it. But again, the question is, are we really simulating the correct numbers? So the model really has to match nature of the measurements. Henrietta, if you'd like to expand on that.
So are these total FTD or just the fresh part?
This is the total.
Total.
Yeah, maybe that's where the problem is. What's interesting, I can fit anything you want. But this basically is what I thought was the total based on what Henrietta and her group. But something interesting here, the radon measurements cannot measure the reversal of the flow, right?
Yes.
So here is the lowest is 0, but the model can give you the reverse, like the water going from the ocean to the, okay, so the flow can reverse. Anyway, we're still talking about this, and maybe if we use fresh components, that can be better. Another difficulty is that my simulations are average over the whole shoreline. But actually, your measurements at points, so maybe we can just work that out. So, but basically, I have the fluxes. These are the fluxes, meter cube per meter per day, and I have salinities at different times. So basically, we can easily calculate the freshwater. But what happens when you have reversed flow? How do you estimate the fresh? No. So in modeling, it will be 0 at this time, right?
Yeah, if you have reverse flow, you should not have discharge.
Yeah. Okay. But we found something interesting, which is because the tides, you have flow in and out because of the tides. So actually, it seems like the SGD change with tides is cyclic. It doesn't follow the same path. Maybe I can show you the next one. So the circles are the data, and the solid line is the model. So basically, as you have tides, this is like rising tide, and this is declining tide. So they don't follow the same path up and down. So it seems like they follow different path as you go high tides. So you have decline along this line here. If you have rising tide, they increase, this. Again, declining tide, so you have increase in SGD like this. That's because of the rate of change of tides which controls the flow. So it doesn't follow the same path. I think that's a reasonable explanation because the model provides this lines here. So this is when it's basically rising the tide, follow different path from the declining tide, which is interesting. there is a couple papers which talk about modeling. I don't know if I thought maybe some people might be interested in that. I thought this one interesting because they talk about when the models work well, when they don't. And this paper talks about when models can work better with which techniques. Suggest we take a look at it. It includes Friedman's assessment. And this one is actually a field site modeling. So this is kind of old, I think 2007, but there's some interesting results. The site in Louisiana, and this is a plan views, the ocean is here. And this is a cross section with different layering, ocean side, land side. And they solve the same equations I showed you for density dependent. And they have results like that. So that's basically in and out. Like this is SGD out and SGD in. So depending on where the location is. And they had some density data for water to compare with to use as validation. But I don't think they have SGD data to compare with. But they managed to publish it. Okay, any questions? Now to see the models. So that's basically the model modeling domain. So we see all the pictures here and all the data here. So if I can show you maybe this model. That's not the correct one. this is a model for Kyoto. So you can see at the top there is models that you can choose from. So we have mud flow there. We have mud bath, which is particle tracing model. So you can inject particles and see where they end up. And there is MET3, which is a solid transport model that includes convection dispersion. Then CWAT, which is a density dependent model. It's basically CWAT is combination of MET3D and mud flow. So that combines the two together to do the density. So you can, the setup is really nice. You can change it, choose between different models, run them, set them up after you create the conceptual model.
So is path what you use to determine like the 2 and 10-year boundaries?
Yes. So you just inject large number of particles and see them disperse or convect actually, convection dispersion. Then outline the area. It is eating lots of data because we have tides, so this is like very high resolution tides. We are almost done, just to look at this.
How much computing power do you use? What's ideal? You know, sometimes people go, gee, I wonder if those groundwater models would want to use a supercomputer on Maui. That's, people have said that to me.
Yeah, yeah.
And I go, I don't know.
Yes, actually that would be ideal because there is two issues here: the storage, the CPU, how much storage you have. So sometimes the computer cannot accommodate that. And if you have large domain with small cells, then you have the storage has to be
The
extensive.
storage, does that mean memory?
Yeah. So sometimes the computer cannot accommodate that.
Mhm.
So there will be limit on how many cells you could have.
Mhm.
The other thing is if too many cells require too much calculations, and especially nonlinear calculations, trial and error, so the computer would be slow.
Mhm.
Like, I think one run of this takes hours, but that's not too bad. That sometimes it takes forever.
I've had students that work with you and they say, you know, had to run all night. The
Yeah.
program had to run all night long.
Right.
But if you have a direct feed into a
Should
high
be-
performance computer, you can
Be fast.
pump it out in half an hour.
But there is a problem with that. Sometimes the model itself is not parallel programmed in a parallel way, so it will be just faster. But if you want to use supercomputers, the model should be run or should be written for that, to use many processors at the same time.
Uh-huh.
So that would be fast. And actually this one, Modflow has a parallel version, so I run it, it is faster than the regular.
Mm.
So here's the results. So you can see multiple windows here. This one is the area, the model area itself. So you can see the wells are there, the boundaries are there. So you have to set the boundary condition here. There is a buffer zone with shoreline, and this is in the ocean. And basically, This is what you have as a conceptual model, with the information in the conceptual model of that. Like say, the template is just something you copy to create different problems. But I have the sources and sinks include all the wells and boundary conditions, conductivity zones. I have a recharge map and observation wells for water and for salt, and etc. And there's some data by this person here, Paul. So you can really shut this off and turn on one by one. Like this is the boundaries, and here is the conductivity zone, and you can everyone active, and each one has you can assign values for conductivities here. So each zone will have different conductivities. This is the geology. So you can have as many zones as you are available. Then once you run, you include all of that and run the model and get it to work. And you can look at the results like this. So basically, this is water level after the simulations and after all the calculation. So the ocean side is 0 and the mountains are high. And by the way, this was for recharge maps that looks like this. So this is like the recharge map, so each area has different recharge. Then you can look at the time variability. So this one, we have Kiholo well, which has some data in it. I don't know if you see the different colors. The lighter one is measurements, and the red are simulation. See, this is some sort of calibration. So the measurements agrees roughly with measurements. Then this one here is basically the 45 degrees, and you can see lots of scattering, but it's not too bad. Actually, we try to improve on this now. Then this one here is the SGD. So this is at the shoreline. So this is fluctuation of the SGD with time at the shoreline. So the model gives you that. And if you want to go to the bottom of the ocean.
The bottom of the ocean.
Yeah.
Let's go.
So you can do this. So actually, relatively speaking, most of the SGD comes at the shoreline, which is in good flavor.
Now it does.
Yeah. So basically, you can do also like monitoring at different locations. So I can show changes at any location of salinity or water level. So basically, the bottom line here, we have some flexibility in setting up your aquifer, and the better data is, as more data is better in setting up the model. And you can do scenarios. Basically, for example, I can remove that recharge and add different recharge, like under climate change. Very easy. I can turn one off and on easily and run the model to when you save it, the model under different names, it will keep all of that. So you can easily click on this one, see, yeah, here is what climate, here is without climate change, here is land use, etc. So you can compare all of that. But again, the bottom line is you have to have accurate data to support all of that. Okay, so basically, you have to use data to the extent to get reasonable. Okay, that was too long for you, I'm sure, but not for me.
Keep going.
Any questions?
So the connectivity and the recharge, all those, are those just shape files that you made in GIS and brought it into the program? Oh, okay.
So basically, you can import the GIS from that website I showed you, from the state, and read it. So actually, here is a GIS layout. See all of these GIS coverages. So I can just convert it to this easily. So like the cost line, I can read the shape files and read it.
So does it read data that's stored in the shapefile?
Yeah.
Or is it, like, can you have like connectivity saved already in the shapefile? Or
Yeah,
you have
you
to
can
still go in
do
and assign?
it both ways.
Oh.
So that you create any special data file and you can export it as a shape file as well. Okay, like for example, the domain and like say I created some recharge data or whatever, I can export it also in shape. But this program reads shape file directly, but you have to convert it to whatever you want in the current. Like this one, like you see the recharge map. Okay, I read it as a shape file. Then I read it here, so to that coverage here. So just to convert it. Okay, any questions?
There was areas where the model predicted, but I'm assuming that salt water was going into the land,
Right.
and there wasn't any data points. The people who actually model submarine groundwater discharge, they don't have methodologies to find the amount of salt water that's going into the land as the water lands get pushed up. I mean, like, let's look at Puna. Is there a way to kind of figure out how much water it takes to flood the streets? If the, if the K value of the substrate is known?
Yeah, it's on the poster right up there, I think.
So how come what you didn't have measurements?
That
Your
depends on the
situation?
method.
I think this was the Korean island that we were showing us. That as the tide came in, submarine groundwater discharge
No,
was.
that was this side here.
Okay, all right.
Actually, you can see it here, the negative positive, because in and out. But what Henrietta talked about last time, she mentioned one technique, I think, if I remember correctly, that can measure reversal, that can predict water from the ocean to the land.
Measure the water level in a monitor. Like it goes up and down, so however much it goes up, there got to be that much water underneath it pushing it up that far.
Yeah.
But there is no direct method.
That's pretty direct.
There is no direct method. Radon will not give you that, right? It will just give you from land.
Radon can give you a lot, whatever.
Right.
It gives you kind of depending on how you frame it.
But that's measuring water level is not accurate, because you need conductivity, you need to model it to calibrate it.
No, I'm just saying if you want a physical, like what volume of water went into the aquifer, then measuring how much water level went up, assuming you say, okay, we're looking at this area and this much the water level went up, all you need, you need to multiply that height by a length and a width, and you have volume. So you just
But
need
you
to
need
estimate the length and the
porosity.
width.
and you need conductivity to do that.
You would need porosity, but not necessarily conductivity. Like, I mean, it's a volume, it's literally calculating a
No,
volume.
but what I am interested in a direct method, that will not have errors. Right? Because indirect error method, you will have multiple errors. But the radon give you a direct measurement of there's some error.
There's
Right,
so much
right.
error,
But at
you
least
might as
it
well not
is,
do it.
but it's independent from, like basically, I can calibrate the model to give you the SG, right? But it would be nice if you give me the SG from direct measurements, that's what I'm trying to do.
Yeah, I mean, it has to be worked on from both angles, for sure. Because the hard part about radon is like, when you measure, it's like, well, where did I just measure SG from? Like, from here, from here too, from over here, from the current, like, you know, there's so much variability that goes into everything, you just have to try and converge on an answer from this many different things.
But how did you say you estimated then, if you have the water level?
So
But
he
yeah.
asked, how do you know, like, how can you figure out the volume of seawater that went into an aquifer? And if you have a water level, you can watch it change with the tide. And if you know the height that water went up, you know that probably that much seawater must have went into the aquifer to push it up that high.
Well, my observation was that the model showed that seawater going into the aquifer, but there was no measurements to calibrate it.
Right, because the radon, it was based on radon, so that is based on radon, yes. And radon measurements does not measure the flow and just measure the flow.
Fair enough, thank you.
Okay, thanks. You can- Okay,